Hey everybody, welcome to section 10.2. And inside of this section, we're going to be comparing two data sets where we know the population means, but we don't know the standard deviations. So this is useful when the population standard deviation is known, but the sample standard deviation, we don't know. This one is rather uncommon because if we're given a data set, oftentimes we're just given a data set, we can calculate the population or the sample standard deviation just from using our calculators. But for whatever reason, this time we know the population standard deviation, but we don't know the sample standard deviation. And we have our formulas here. Formulas look pretty similar to the previous ones. And let's go ahead and practice this. So we know we're using these formulas when we have the population standard deviation. We don't have the sample standard deviation. We can go back here. We had data sets for our last one. So here the difference is sample standard deviation. That's what we did in the first lesson. All right, so here we go. We are looking at two different WACs. Or what are we looking at here? 20 floors. 20 floors are randomly assigned to test each wax. And we're testing how long the average lasting time of the floor waxes. So the wax kind of protects the floor. Sample mean number of months. So the first wax lasts for 3 months. The other wax lasts for 2.9 months with population standard deviations here. So as I look at this, I notice that these look pretty similar. 3 compared to 2.9. That's only what, 0.1 of a difference, so about a third of a standard deviation away. So I'm immediately thinking it's probably not convincing. I'm not convinced that wax 1 lasts longer than wax 2. So to write out our hypotheses, we want our alternative hypothesis is what we want to prove. So that would be the average of wax 1 is greater than average of wax 2. Then the null hypothesis is the opposite of that. So that would be wax 1 is less than or equal to wax 2. Remember, these contradict each other, and the alternative hypothesis is what we want to prove. And so here it's using our distribution and using these population standard deviations and the sample sizes. They calculate the p-value. Good news for us is we do not need to calculate this by hand. We're going to calculate this using our handy calculator. So we can plug in, and this is provided in our notes. There's a sheet that shows which calculator to use. So we can plug in our data, and it tells us 0.366. And this calculator is always going to be giving us a two-tail result. It doesn't give an option, so this is a two-tail result. So, but this, all these hypotheses statements are going to be a one-tail test because we're looking for the average of 1 to be greater than the average of 2. So that's looking at just one side. So what we need to do is take this probability and divide it by 2. So we take that 0.36, cut it in half, we get about 0.18. P-value is 0.18, which is a very common result. We were testing this at the 5% significance level. So it needs to be less than 0.05 to reject. It is not less. So therefore, we don't reject the null hypothesis. And so we would say there's not statistical evidence to show that wax 1 lasts longer than wax 2. All right. We're going to look at some senators, U.S. senators, and they claim U.S. Democrat U.S. senators are older than Republican U.S. senators on average. So they're going to look at 30 randomly selected Republican senators, and they get their average age of 61.675 years, with a standard deviation pretty big, 10.17. Then the mean age of 30 randomly selected Democratic senators was 61 years, 61.704 years, with a standard deviation of 9.55. And we want to answer the question, does the data indicate that Democratic senators are older than Republican senators on average? Test at the 5%. So Democratic senators are 61.704, and Republicans are 61.675. So if we look at those two numbers, wow, those are shockingly close to each other. We even have large standard deviations. So immediately when I look at this, I do not see Democrats being older by very much at all, very small amount. So based on our data on this, I would be shocked if this is a reject. And for this problem, they don't tell us we have the population standard deviation. They say we just take the 30 and we calculate the average and we calculate the standard deviation. So for that, we don't have the population standard deviation. We have the sample standard deviation. So that's going back to our 10.1. That's using this calculator, which is just using the sample standard deviation. So we can plug in our numbers. This is a one-tail test because we're checking to see if, the Democratic US senators are older than the Republicans. So just one tail. And look at that, we find out that this is so common. This happens about half the time. So, this is bizarrely common. So there is no chance at all that we're able to statistically justify this result. So we don't reject the null hypothesis. In fact, we maybe even could make a statement talking about how common this is and how close they are. All right, so that's the first part. The next lesson is going to talk about 10.3, population proportions.